Okay, so before we go further on state space, how to derive the state space, we have to know some of the definitions that involve in state space technique. So the first one is linear independence, whereby a set of variables is said to be linearly independent if none of the variables can be written as a linear combination of the others. Okay, so that's one of the prerequisite of the state space. And then there's a system variable, which is any variable that responds to input or initial conditions in a system. And then there's also state variables, which is the smallest set of linearly independent system variables, such that the values of the members of the set at the time t0 along with non-forcing functions completely determine the value of all system variables for all t bigger than t0. And then there's also state vector, which is a vector whose elements are the state variables. So if I read from here, maybe you're not so clear what are those. So let's have a look at this page. Okay, more definition, which is a state space, is the n-dimensional space whose axes are the state variables. And then there's also state equations, which is a set of n simultaneous first order differential equations with n variables, where the n variables to be solved are the state variables. And then there's also output equation, which is the algebraic equation expresses the output variables of a system as linear combinations of the state variables and the inputs. So from here you could see, for example, this is the state space, and you see here, for example, in this case there's a VR and VC as the state variables. Okay, and let's say there's a state vector trajectory whereby a system that goes from here to here or from here to here, and at this point it is defined by this state vector, and there's another point it is defined by this state vector. So this is called a state vector where I have the coordinates. This coordinates is defined by this state variable. So all of this is the state space. So this is a graphic representation of state space and a state vector. So in a state vector, you will find out the state variables. Okay. Then we have in state space representation, there's always only two equations, which is the state equation and output equation. If you could see here from this definition, the state equations and the output equations. Okay, so those two are important in to derive that state space representation. Okay. So why they involve only two equations? Because we only deal with the current state with respect to the input and the output state. So if you could see here, for this representation, t is always bigger or equal to t0, and initial conditions x t0, where x is the state vector. If you could see here, x, both x at the state equation and output equation, that's x state vector. It contains that state variables. Okay, and then x dot, which is here, is derivative of the state vector with respect to time, and it is always the first derivative. So x dot one dot here is first derivative. Okay, so if 2 dot means 2 second derivative, first derivative, second derivative. If 3 dots mean 3 derivatives. So but in state space representation, we always interested the x dot only the first derivative as the main subject. So we will make sure that we put the first derivative at this left hand side. And then y is the output vector, u is the input or the control vector, which is here. It involves two equations here. And then A, B, C, and D, if you could see here, all of them are metrics. So you have 4 metrics. The first one is the system metrics, and then B is input metrics, C is output metrics, and D is feed forward. So most of the cases, it can be ABC without D, there's no feed forward. And in some cases, there are D with feed forward metrics, okay? So apart from that, okay, what you have to know and bear in mind if there's translation and electrical networks problems, you have to identify the energy storage elements. Basically in translation, there's 2, which is spring and mass. So both of these store energy, but viscous damper, it dissipates the energy. While in electrical system, okay, the one that store energy is capacitor and inductor, while the resistor, it dissipate and dissipate the energy. So that's why when you have the resistor in the circuit, that resistor will become hot, okay? So because it dissipates the energy, okay? So this is the basic thing that you have to understand. And then, okay, so how do we come up with that general state representation? So for example, we are given a differential equation as follows, and we want to transform it into a state space representation. So you have this, m is the mass, and d squared x over dt squared is supposed to be squared here. Sorry, I left this out. And then d, which is the damper, dx over dt, and k is the spring, x, and equals to f, which is the input. So from here we have to identify the input, the progressive states, and the output state, okay? So from here, xt, xt, and xt are the output, okay, and ft is the input. So remember, when we did the frequency domain, we changed xt to xs, xs, and xs. And then once we want to find the transfer function, it's always the output over input. So xs over fs, which is this input. And then you have that system. So it's basically nearly the same, but in this technique, we have to assume some of the cases. So these are some of the few simple steps that we have to go through. The first one, we have to rearrange the equation, which is in this case the second derivative as the subject, okay? So again, I left out, it's supposed to be d squared x over dt squared. I left out the squared thing, so please take note on that. Equals to minus dx over dt minus k, and then the input ft. And then you simplify it by make it, we want to eliminate this m at this side, so we divide m on the other side. And what we assume here is that xt we assume equals to x1, okay? So that x1, we put 2 dots which represent the second derivatives. So if it's 1 dot, it is 1 derivative. If there's no, we just put as x1, okay? So basically from here, we get this one once we assume xt here equals to x1. Okay, that's the first step. And then next we reduce it to first derivative. So the last time we assume xt equals to x1, but this time we assume x1 dot equals to x2. Okay, so once we have this equation, we just substitute it in here. Okay, we substitute here. Okay, so if you could see here, if we have x dot 1 and x2, if we do derivative of both sides, it will become x double dot, x1 double dot, and x2 1 dot. Okay, and then we just replace it here. So x2 1 dot over here equals to d over m, and then x2 minus k over m x1, and then 1 over m ut is the input. So from here we got state equation 1 and state equation 2. So once we done that second step, we need to define the matrix size based on the system order and fill up in the coefficient of the state vector. So state derivative into the matrix according to state equation 1 and state equation 2 as below. So I'm taking this one back from the last equation. So x1 dot equals to x2, which is the assumption of this one. Sorry. Okay, this one is the assumption that we assume x1 dot equals to x2. So that is your first equation, and the second equation is from after we substitute this one into the last equation, so we get this one. So we're interested to look at this equation and this equation. So we want to put it in the matrix. Okay, so we have x dot 1 here and x dot 2, x2 dot, okay, equal to, which is this one. So in this equation, okay, the first equation, there's no value of x1, there's no x1 term, so it's 0. Okay, but there's a x2 term, okay, over here, so it's 1. We put 1 here, and then x2 dot goes to this line, okay, this row. If you could see here, there's x1 term, which is here, represented by here, so it's negative km times x1, you get this term. Okay, and then there's x2 term as well, which is this. Okay, so negative d over m times x2, so you get this. So this one is your matrices over here, and remember we have that input ut, so we plus, and then for this one, okay, it's 0 over and it's 1 over m. Okay, because it's represent this equation down here, x dot 2, so it's the bottom one, not the top one. Okay, okay, moving on to the next step is that the fourth step is that we have to define the output equation. So since we are interested in xt, okay, and we have assumed that xt equals to x1, so basically y, which is the output, is x equals to xt and equals to x1. So this one is the output equation. So once we want to put in the matrices, what you have to do is y equals to, so there's only one column, there's only one row but 2 columns, because the first column represents x1, okay, the second column represent x2 because 1 times x1 you get this x1. Okay, 0 times with x2 you get 0. So we basically want to write this equation in matrix form. Okay, so you write it as this one. So 2 by 1 matrix with 2 1 by 2 to 2 by 1 matrix. Okay, plus with this input, because since the output equation is just this one, so this one basically is just 0. So that is your fourth steps. So once we have that, this matrix, okay, this output equation matrix, and you have which one was it, and you have this matrix. Okay, so basically the state representation of the system is represented by this one, which is that state equation, and represented by this one, which is the output equation. So once the question asks to put it in the state space representation, you always have to come up with these two sets of equation. The first one is the state equation, and the second one is the output equation. Okay, so there you are.